So far, we've been talking about rate of change in a general sense. Now, let's connect this to something physical. One of the most common examples of rate of change is velocity. Velocity measures how position changes over time. Let s of t be the position at time t. The average velocity over the interval from a to t is s of t minus s of a over t minus a. This formula should look familiar. It is mathematically identical to the slope of a secant line. Change in position divided by change in time. That's just average rate of change. If you drive 100 miles in 2 hours, your average velocity is 50 miles per hour. That doesn't mean you are driving 50 miles per hour the entire time. It's just the average over that interval. This is exactly what a secant slope measures. But what if we want the velocity at exactly 1 moment? What is your speed at exactly 3 seconds? We can't use the interval if we only want 1 instant. The instantaneous velocity at time t equals a is the value that the average velocities approach as the time interval shrinks to 0, provided the value exists. Let me say that more simply. We compute the average velocity over the smaller and smaller time intervals. As the interval gets smaller, the average velocities begin to approach a single number. That number is the instantaneous velocity. This process of letting a variable approach a value is called taking a limit. A limit describes what a value approaches. This is the key idea that connects everything in calculus. Now, let's apply this idea. We're given the function h of t equals 2t squared minus 4 at the point t equals negative 3. That means we want the slope at exactly 1 point. First, we need to identify the point. We have the input is negative 3. What is the output? We are going to replace t with negative 3 to find the output. Negative 3 squared is 9, and 9 times 2 is 18. 18 minus 4 is 14. So the point is negative 3, 14. To estimate the instantaneous rate of change of this point, we'll compute the average rate of change near t equals negative 3. T equals negative 3 is here, so I'll pick the input that is very close to negative 3. It could be negative 2.9 and negative 3.1. When the input is negative 2.9, the output will be h of negative 2.9. So I'll replace t with negative 2.9 to find the output. And that point is negative 2.9 comma 12.82. To find the average rate of change between these 2 points, I'll use the formula of the slope of the secant line. I'll take 12.82 minus 14 over negative 2.9 minus negative 3. And my slope is negative 11.8. Then I pick a value that's slightly less than negative 3, which is negative 3.1. The input is negative 3.1. To find the output, I substitute negative 3.1 in for t to find h of negative 3.1. And I get 15.22. So the point is negative 3.1 comma 15.22. And I use a slope formula to find the average rate of change. The numerator is the change in the output. So I take 15.22 minus 14. And the denominator is the change in the input. I take negative 3.1 minus negative 3. And I get 1.22 divided by negative 0.1, which is negative 12.2. From the right side of negative 3, the slope is negative 11.8. From the left side of negative 3, the slope is about negative 12.2. Notice something? One side gave us negative 11.8. The other side gave us negative 12.2. As we choose values closer and closer to negative 3, these slopes will get closer and closer to a single number, and that number appears to be negative 12. So the instantaneous rate of change of this function at t equals negative 3 is negative 12. So here's what we just did. We use secant slopes to estimate. As the interval shrinks, the slopes approach negative 12. That is the instantaneous rate of change. And that's exactly what a limit gives us.